Ok, bah alors bonjour, et donc je suis ravi de vous retrouver. J'espère qu'on va avoir un superbe exposé comme le précédent. Donc, I will speak English now for you because, comme l'exposé précédent, hein, ce sont des étudiants de Roumanie, de Cluj, qui vont nous faire leur exposé qui s'appelle ABRACADABRA. So, I am pleased to introduce you, and I hope you enjoy your talk. So you can go now.
So, hello, I'm Daria Jidavu.
And I'm Diana Haranbash.
And our research topic is called Abracadabra. And the problem sounds like this. There is a word composed with the letters A and B, which evolves in such a way that in each step, A becomes AB and B becomes A. Therefore, if we start from A, as you can see in this image, it will turn into AB, then AB will become ABA, then ABA into ABAAB, and so on and so forth. We had to find out how will the word look at the nth stage, if we can say it exactly or not.
So the first step of the solution is actually rewriting the problem. So we defined an array of words called Tn, with T1 being equal to A, which is the first word. And then let f be a function that turns A into AB and B into A. Obviously, if you apply the function on a word, you'll obtain the next one. We also introduce a new operation, which is associative but not commutative. So the order of the elements matter. And this works as a concatenation. It's visible that while discussing concatenation, the function f becomes additive, as you can see in this relation. So let's now talk about the recurrence relation. We observe that T3 is actually formed from T2, followed by T1, and also T4 is T3 concatenated with T2, T5 is formed by the fourth word, followed by the third one, and so on. So it's safe to state that a word is formed by concatenating the last two previous words, as you can see here in this relation.
We studied further the number of letters in each word, and for this we consider two arrays, A for the number of A's in each word and B for the number of B's in each word. We wrote down a few examples. The first word is A, so the number of A's, A1, will be 1. The number of B's, B1, will be 0. Second word, AB, 1A, 1B. Third word, ABA, 2 A's, 1B, and so on and so forth. Seeing this, the Fibonacci sequence comes to mind. It is defined by the law you see there, so each number represents the sum of the two previous ones. Therefore, if we start from 0 and 1, the next number in the Fibonacci sequence will be 0 plus 1, which is 1, then the next one, 1 plus 1, which is 2, the next one, 1 plus 2, which is 3, and so on and so forth. We arrived at the conclusion that for each word, the number of A's is fk, the number of B's is fk minus 1, and the number of letters, the total number of letters, is fk plus 1. I will show you on this picture to be more clear. So on the left side, we have the Fibonacci sequence, and the words in our problem are in brackets on the right side. The first word is A. 0 represents the number of B's, the first 1 represents the number of A's in the word, and the last one, the number of letters in the word. To be more clear, let's take another example, the second one. The second word is AB, and we are only interested in the last three numbers of the Fibonacci sequence on the left. So the first one represents the number of B's in the word, the second one represents the number of A's in the word, and 2, the number of letters in the word. Let's take one more example. Third word, ABA, and again, last three numbers from the Fibonacci sequence. 1, as there is only one B, 2, 2 A's, and 3, 3 letters in total.
Okay, so now we tried to find a general form of an element. So we defined a series of laws, functions, and arrays so that we can turn a word into a binary number by transforming A into 1 and B into 0. So as you can see here, A becomes 1, AB becomes 1, 0, ABA 1, 0, 1, ABAAB 1, 0, 1, 1, 0, and so on. Then we defined an array called n that actually is the transformation of the binary word, binary number into a decimal one. So in base 10, 1 becomes 1, 1, 0 becomes 2, 1, 0, 1 becomes 5, and 1, 0, 1, 1, 0 becomes 22, and so on. Sorry. So we keep in mind the recurrence from forming the words. That was that a word is actually formed by concatenating the last two ones. So after the transformations, we have a new recursion relation, which is this one. It may seem a little complicated, so we decided to try to find another recurrence relation that can be easier by attaching the characteristic equation, which is this one, with the discriminant equal to 2 at the power of the n-1 Fibonacci plus 4. As we can see, the possible two solutions, T1 and T2, are these ones. And as none of them is a constant and they both depend on n and elements from the Fibonacci sequence, we can conclude that there is no simpler form of the recurrence. So we'll keep this one. We cannot find a general final form of a word.
I'd like to show you now a generalization of the problem. At this point, we no longer consider that we start from A. So we keep the notation from the beginning of the presentations, and we have the relations, these two relations. The number of A's in a word is equal to the sum of the number of A's in the two previous words, and the number of B's in a word is equal to the number of A's in the previous word. But now A1, so the number of A's in the first word, and B1, both depend on the form of the first word, so T1. Let's now consider T1 as the number of A's, let's say C1 A's, followed by D1 B's. And just like this, till we have X groups of A's followed by X groups of B's. Now we can easily observe that the total number of A's in this word, so A1, will be the sum of all the C's, and the total number of B's, B1, will be the sum of all the D's. Let's discuss a bit about the formation of the word in this case. Keeping in mind that function of B is equal to A, as it's given in the problem, we realize that applying the function n times to B is similar to applying the function n-1 times to A. Let's now consider another function, call it h, with two arguments, n and p, which represents the concatenation of p functions of A at the power of n. Now, the formula for generating the nth word looks like this. Function of T1 at the power of n is equal to the concatenation of all h functions applied to n and the c's, respectively to n-1 and all the d's. Let's discuss an example. I took a random word, let's say 2 a's, so C1 is 2, 3 b's, D1 is 3, 1 a, C2 is 1, and 2 b's, D2 is 2. I wrote down the formula from above, you can see there, and then I applied it on this example. So we have the concatenation of two functions of A at the power of n, as C1 is 2. Then we have the concatenation of three functions of A at the power of n-1, as D1 is 3. And just like this for the other two functions. Now, as there is only one transformation, so we try to obtain the second word from the first one, n will be equal to 1. So function of a at the power of n is practically function of a, which is ab, as given in the problem. Function of a at the power of n minus 1 is, as I mentioned before, equal to function of b at the power of n. And this is function of b, as I said, n is 1, so function of b is a. Now in this last line, you can see the final result, which obeys the law given in the problem.
So to sum up with, we decided to tell you a little bit what we worked for a year, just in a nutshell. So every result is going to be presented here in an easier form. Using mathematical induction, we proved that our words follow the Fibonacci sequence. So a recurrence based on two previous elements of the sequence can define the array. There is no general recurrent expression that can show the final form of our word, though. And also the number of letters A and B and the total number of characters follow the Fibonacci rule, and they can be calculated. So I think that's all. So thank you for your attention.
Ok, donc, eh bien, écoutez, je vous félicite. I congratulate you for your speech. It was very interesting. And we'll take some questions from the audience. So, first question, you said that it's safe to say that the Tn plus 2 is the concatenation of Tn plus 1 and Tn. But did you prove it? You just show on the first example that it was always the case, but do you have a proof that it's right?
Yes, we have a proof. It's it's proved by mathematical induction in a really easy way. So we decided that as it's easy, we shouldn't actually put it in the presentation, but it can be done in about 5 minutes, let's say.
Okay. So another question, the growth rate of your word is, can you tell us something about the growth rate of your word? You said, what is possible if you change the rule? I tell you the question. Can you say anything about the growth rates that are possible or impossible when you change the rule? For instance, 2 to the n, or n to the 2, or factorial n. I don't know how to say that to this in English. Now you understand the question? Okay.
Yes. Well, actually, for the example that we studied, which was beginning with A, we got the Fibonacci sequence, and as you can see, it kind of grows in using the Fibonacci rule. But for example, if it's just a random word, then probably it will actually, it's not Fibonacci, the usual Fibonacci, but still it will follow some kind of rule. This one with addition by concatenation and adding two elements. So I'm not sure if I understand clearly the question, but I think that
Me neither.
I'm not sure.
Okay. So so you said it's not clear. We cannot have a general form for the number. Is the integer number you associate? No. Okay. When you have a sequence, a word, you come with your construction with a binary to an integer number. Then you put it in a base 10, and then okay. You said we don't have any formulas for this, but it's not clear for us that you didn't find a formula, but how can you say there isn't any formula? You know, you said it can't exist. Are you sure of that?
Well, we tried, we have a second grade not equation, a second grade recurrence relation, and we try to make it a first grade one, so that we can find, by using a first step, not just using two previous other elements, we tried to find just one grade, just to be a to be a first grade recurrence relation, and it is not possible to be found because of the solutions that we get from T1 and T2, as none of them is a constant and they both depend on different other sequences and on n. So we can't really, from the first two words or something like this, we can't come to the conclusion that we find the nth word without using more than just one information. So we need both arguments. I'm not sure if they're called arguments in English in this case, but we need a second grade recurrence relation. We cannot find a first grade one.
I have to say I'm impressed with your knowledge about sequences. I'm quite sure you know more about sequences than most of my students, which are in university. But in fact, the method you suggest, which is quite smart and we can help to find a lot of formulas with sequence, maybe it doesn't work in this case. That doesn't prove there is no other way, very sophisticated way to find a formula, you know. But okay.
Yeah. Yes, but that we know from high school, and actually we're in the 10th grade, so that's all we can do. I'm not probably.
But it's very impressive. It's amazing. Don't worry. The audience is also amazed as me. I'm sure of that. Okay, you said some people said you made an integer with your binary sequences. But you could also make a real number with this, or rational number if you put a comma somewhere. Did you look at things like that?
No, actually, I think it will be a little bit more complicated if we try to make rational numbers with that fractional part. I'm not sure.
Okay.
It was an easier method, and it's an interesting question. Well, we're gonna continue studying on it and researching.
Okay. Are you able to say how many A and how many B are in a word of n letters?
Daria, this one is to you.
Yes, we can say it, but as Diana said, it kind of depends on the previous words. So you have to know which Fibonacci number corresponds to the word. So if you have the nth word, you need to know the nth Fibonacci number in order to say the number of letters you have in the word.
So the question is, maybe, do you know how to compute the nth Fibonacci number without computing the n-1 before?
Without knowing the previous numbers, no, I don't think so.
It's not an easy exercise, so it's understandable, and don't worry. Okay. Okay, so I think it's I said everything. Donc, I will thank you for your speech. I'm very glad to have heard you. It was very, very interesting, and I will think about it. You know, my curiosity is now. I want to look at this sequence. I want to think about it. I'm not sure I will find something, but I think tonight I will look about it. So, okay, thank you very much for this. It was very, very nice. Bye-bye.
Bye.
Bye.